So our next talk is a data-driven approach of uncertainty quantification on Reynolds stress based on DNS turbulence data.
Thank you. Hi, everyone. My name is Amy. I'm a PhD student from the University of Southern California. Today, I will introduce a data-driven approach to uncertainty quantification of Reynolds stress. So the background is that we have plenty of simulation data, but we lack ways of retrieving useful information from those data. So this problem, there are several difficulties in this problem. First, it is multivariate. So for each point in the flow field, we have velocity, temperature, pressure, and many other quantities. Second, the flow field is evolving spatially and temporally since it is the solution of a set of PDEs. Third is very high dimensional. Imagine a snapshot of DNS simulation, direct numerical simulation. It could be several gigabytes. It's very high dimensional. So to address those problems, we propose a framework, which I will go through step by step. So the first is that we have a flow field, which could be high fidelity simulations, for example, a large eddy simulation or direct numerical simulation. It can also come from experiment measurements. So the idea is instead of modeling the whole flow field, which is very huge, we try to focus on some representative volume elements, which we refer to as RVEs. And those RVEs are essentially the information carrier of the flow field. And we try to model it via stochastic field theory. After we sample those RVEs from the flow field, which is those small black squares here, which uses Karhunen-Loeve Expansion to decompose the RV into different modes and only keep a few modes to build a surrogate model from the few modes to the quantity of interest that we want to predict. And we use polynomial chaos expansion in this case. This slide shows a mathematical foundation of Karhunen-Loeve expansion and polynomial chaos expansion. So for the sake of time, I just skip it. Let's look at the results. First, remember that we said we only keep a few Karhunen-Loeve expansion terms and we through the data. So the first question is how well those few Karhunen-Loeve modes represent the original data. So the left two figures shows the comparison between KL representation and the original data for the training data set and the test data set. As you can see, they matched very well. Then let's look at the performance of the surrogate model by our PCE. The top figure shows a comparison between predicted result by PCE and the truth value. As you can see, almost all the points are clustered near the diagonal line, which means the prediction is pretty good. And for the sake of uncertainty quantification, we also plot the probability density function for the Reynolds stress for 6 components because it is a tensor, it is a symmetric tensor, so there are 6 components. So this is for isotropic turbulence flow. We also apply the same framework to channel flow, which is fundamentally different and very important in many engineering applications. For example, in aerospace applications, the channel flow is very important. As you can see, the results are still very good, which proves that this method is very robust. Similar to most machine learning techniques, people often want to know how well your method converges versus number of training points and versus number of KL modes. So this slide shows the convergence study for number of Karhunen-Loeve bases and number of training points, and we found the optimal points for both parameters. The last very important parameters in this framework are the size of the RVE. As you can imagine very intuitively, if you have a very, very small RVE, which only contains, for example, a few fluid particles, you can, almost all the points have the same velocity and temperature. As you can see, so there contains very little information in this RVE. However, if you increase the RVE, the RVE contains more information. It can feel more about the surrounding flow field. However, the dimension of the problem increased very large. So there is a trade-off between the size of the RVE. So this slide gives a qualitative study of the size of the RVE. And this next slide shows a quantitative effect of the RVE size for our framework. So if you are interested, I can explain it in the poster section. So give you a summary that we build a PCE surrogate model for this fluid problem, which is very high dimensional. We build a surrogate model by dimension reduction, by Karhunen-Loeve expansion, and then we build a surrogate model by a polynomial chaos expansion. If you have any questions, please feel free to ask.